Hello everyone, I'm Xinyang Li from the Institute of Metal Forming at the RWTH Aachen University. Welcome to the presentation of our work Design of Caliber Rolls Incorporating Load Path Dependent Damage Evolution. I will introduce you our study in these sections. First, I'd like to introduce the background of this work. Why designing a caliber rolling process considering damage evolution is needed. Afterwards, I will explain the simulative method we proposed in this work. And then I would like to show you our result and some discussions. And finally, the conclusion and outlook. So the first part, background. Caliber rolling is an important process to produce semi-finished products in the process chain of bulk metal forming. The billet or rolled from continuous casting is rolled by caliber rolling and is followed by other forming processes like warm or cold forging. Then with some machine processing, the components can be produced. As a key process of the process chain, the internal damage in the material from previous process can be reduced or increased by different loading conditions in caliber rolling. Also, new damage could be induced in this way. The picture at the bottom left shows us two types of defects, chevron and rolled-in scale. The damage can reduce the formability of the material in the following forming process and can influence the mechanical properties of the final components. For instance, the picture at the bottom right, we can see some inclusions after rolling clearly. So it's important to optimize the design of a caliber rolling process. In general, a caliber rolling process consists of several rolling passes. It allows high flexibility regarding process design. It's possible to change the configuration of intermediate passes in caliber rolling without affecting the end geometry. This picture at the bottom left shows us three different routes of a caliber rolling process, which consist of two passes. They have different intermediate geometries, but the same initial and final geometry. This flexibility can influence the filling degree in the intermediate passes and can even lead to filling problems like overfilling and underfilling shown in the right picture below. So the filling degree should be considered in the meantime as a design aspect. This flexibility, changing the design of the intermediate passes, can also influence the load regime and stress distribution in the workpiece. So it's possible to take this influence on the evolution of stress distribution into consideration when we design the rolls of a caliber rolling process. Here we use load paths to characterize the evolution of the stress state with two parameters, the stress traxality and the load parameter. The stress traxality refers to the hydrostatic stress and the von Mises equivalent stress, and the load parameter refers to the third invariant of the stress deviator and the von Mises equivalent stress. The varying of the load path can influence the evolution of damage inside the material within the process. In this way, it can give us the possibility to control the damage using a specially designed caliber rolling route. So not only the filling degree in each pass, but also the damage level can be optimized by altering geometric features of the caliber roll profile in the design stage. In this way, I will introduce you an approach which is purely simulative to optimize routes of caliber rolling for not only the filling degree but also the damage evolution by changing intermediate geometries. In this simulative study, we investigated a four-pass caliber rolling process consisting of round-over-round sequence as an example. This roll sequence is frequently applied in the industry because of its favorable temperature distribution and smooth operation. In this process, the initial roll diameter is 60 millimeter, and the final roll diameter is 40 millimeter. That means an area reduction of around 56% is applied in the four rolling passes. And some process and model details are also shown here. In the case of round-over-round sequence, the access ratio and the area reduction defining these two equations are the most relevant geometric features. And based on a caliber rolling sequence applied in industry, we designed a reference calibration. Here are the geometric features of this reference calibration. We can also see that it has good filling degrees in each passes already, and we started with this reference calibration and do an optimization for it. First is a roll design with regard to filling degree. As I said, caliber rolls are designed conventionally only with regard to the filling degree, which is primarily controlled by geometric features of the caliber roll profile. The definition of filling degree is here. Here an analysis based on FE simulations was conducted to determine the allowable variation of the access ratio and the error reduction, avoiding filling problems. We tried and simulated multiple combinations of access ratio and the error reduction and evaluated the results with respect to the filling degree using threshold of 0.95 for underfilling and 1.0 for overfilling. And here is the resulting matrix of filling degree versus the access ratio and the error reduction for the first rolling pass. Each data point represents a combination of the access ratio and error reduction with different colors, which indicate the filling degree. In this case, the combination colored with blue are a loud combination with adequate filling degree. We repeated this procedure to design all the roll caliber profiles requiring all in all four passes, and then we could establish a range of combination of the access ratio and the error reduction, which ensure proper filling degree. Meanwhile, the influence of access ratio and error reduction on the load path was also investigated with the aim to influence damage evolution in this study. In this design step, we varied the access ratio and error reduction within the range established in the previous section, and to guarantee an adequate filling degree. In order to investigate the effect of each parameter separately, one parameter was varied while the other one was kept unchanged. So we chose three different access ratio from 1.75 to 2.25 with fixed area reduction of 0.25 and 3 area reduction from 0.18 to 0.3 with fixed access ratio of 2. Then we evaluated the evolution of stress traxality and load parameter at a material point, which is represented by a green dot here. Then we can see the effects of the variation of access ratio and error reduction on the evolution of stress traxality and load parameter here. The first rolling pass round to oval and the second rolling pass oval to round are observed separately here, since different stress state arise. As we can see, the variation of access ratio and error reduction can notably change the stress traxality and load parameter at the material point. Generally, we can say a larger access ratio causes a higher stress traxality and a lower load parameter. A higher error reduction leads to a higher stress traxality as well. Despite the difference of values, the causes of traxality and load parameters have a similar tendency with respect to different access ratio and error reductions. According to several studies, a high stress traxality is not favorable in forming because it's beneficial to voids initiation, voids growth, and even occurrence of damage. So, with regard to stress traxality, a higher damage level is assumed to be found with larger access ratio and larger error reduction. In this case, the major design principle regarding damage is to choose the smallest possible access ratio and error reduction while respecting the constraints for a good filling degree as well. And based on the understanding of the influence of the geometric features on filling degree and damage evolution, we could find a new process route aiming to obtain lower damage. Here are the geometric features of the reference and the optimized process routes. The access ratio and error reduction and new process routes were chosen as small as possible. The damage prediction based on the Oyana criterion is also shown here. We can see the new process route shows a good filling degree in each row pass, and we can find similar damage distribution between these two routes, but significantly lower damage levels are predicted in the second and third pass in the new process routes compared to the reference process route, because of the different load paths induced by favorable combination of access ratio and error reduction. We choose these two representative points for some quantitative evaluation because they are obviously different damage values at these two positions. Please note that these 2 points have nothing to do with the material points when we evaluated the load path. We checked the damage evolution at these two representative points on the cross section throughout the two rolling processes. The final damage level obtained after the fourth pass in the new process route is reduced by about 10% compared to the reference route. So it's possible to produce a part with reduced ductile damage while a good filling degree is still guaranteed in caliber rolling by optimizing the design of process. Here comes the conclusion and outlook. In this study, we optimized a 4-pass caliber rolling process, which has two round-over-round sequences, based on a study of the influence of geometric features of the caliber profile on the filling degree and the load path. The results showed that load path variation in caliber rolling can be achieved by changing geometric features of the caliber profile without causing filling problems. For this row sequence, the access ratio of the oval caliber and the percentage of error reduction are the significant parameters for both filling degree and load path. Based on this approach, damage evolution can be controlled in caliber rolling without changing the initial and final geometry, while adequate filling degree can be guaranteed as well. In further studies, integration and evaluation of other existing damage criteria and damage models would be relevant. For caliber rolling, we should consider some models which account for the loader parameter and elevated temperature. Besides, the more efficient and accurate method to optimize the geometries like deep learning or other statistical algorithms are needed. In addition, thorough experimental validation of the results obtained here is necessary. That was our work. Thank you for your attention.